Everybody's talking about quantum computing. But you know what? Let's start with the basics first. So, today we're asking ourselves, what is a qubit? Like, really? Just as a short notice, this video is meant for people without any or without a lot of background knowledge on the topic, so please stay with me. And should there be any questions popping up, please let me know in the comments below. Every computer you've ever used is built from bits. A bit is surprisingly simple. Bit is the short form of binary digits, meaning there is two digits of them. And it's either a 0 or a 1. Basically like a light switch. It's either off or on. And literally everything on your phone, your laptop, and the whole internet ultimately reduces to an enormous collection of these binary decisions. That works amazing and it's great. Okay, so that is today. Now let's have a quick change of scenery. About 100 years ago, a couple of great physicists introduced and developed the new theoretical model of quantum mechanics. I do not want to go into too much detail here, but basically, at very, very small scales, particles behave differently than we expect and what we know from our experience, and we get so-called quantum effects. Quantum particles like electrons, photons, and atoms simply don't act like, I don't know, tiny billiard balls as you could have imagined them, but they work or they function as quantum waves. So far, so good. Now, one could continue thinking that if the quantum particles behave differently than the classical particles we know, then when we would use quantum systems instead of classical ones to store and process information, something remarkable could happen. And indeed, in the early 1980s, scientists started discussing the quantum analogon of computers and bits, the quantum computers and the quantum bits, or in short, qubits. And really, just as with bits and our regular classical computers, the qubits really form the basic unit of a quantum computer. And a qubit is actually very simple. A qubit can be realized by basically any quantum two-level system. Now, a quantum two-level system is basically any quantum system which either has only two levels, such as, for example, two energy levels, or it can have more levels, but we can sufficiently isolate two of them from the rest. So far, so good. Now, there are multiple different platforms being investigated as candidates for qubits and quantum computers, such as superconducting quantum circuits, trapped ions, photons, etc., etc. They all have their advantages and their different disadvantages, and actually various scientific institutions as well as really big companies are looking into them. What you should understand is what makes a qubit fundamentally different from the classical bit is not the hardware, but the physics. Just as with the classical bits, we can write the qubit basis states, that's what we call them, as 0 and 1, and we would call them state 0 and 1, or we can call them ground and excited state, whatever. We use the so-called Dirac bracket notation. Don't care about it for now, just so far so you know, this plus is not like a regular plus, but we will come to that in a bit as well. beautiful way to visualize a qubit is with something called a Bloch sphere. So imagine this being 3D, please, guys. Every possible pure quantum state corresponds to a point on the surface of this sphere. Classical bits can only sit here at the poles. Qubits can point anywhere. There are some really amazing quantum mechanical effects coming with qubits. A qubit can exist in a so-called quantum superposition, a state that is basically a linear combination of 0 and 1, and that is what our whole quantum state tells us here. So basically, a quantum state psi corresponds to alpha state 0 and beta state 1. And this equation contains almost everything. Alpha and beta are complex amplitudes, and their squares correspond, or their squares describe the probabilities of finding the qubit in the respective state, either 0 or 1 when being measured. So alpha and beta describe the quantum state before a measurement occurs. So basically, they defined your qubit state, where your qubit would sit on the Bloch sphere surface. Okay, so I've said that alpha squared and beta squared correspond to probabilities. Now, everybody knows probabilities, right? You leave the house and you think to yourself, man, did I turn off the light? Like, is my light switch in on or off state? I most probably turn it off though, so let's say 80-20, whatever. Yeah, that's not the same probability as an odd qubit. With your light switch at home, the state is clear. It's deterministic. This light switch at home is either on or off. The reason you are using probabilities for your light switch is that you simply don't know it. The switch has a state, and we don't know it. In very harsh words, the reason for probabilities in our classical world is our lack of knowledge, or if you say dramatically, our ignorance. Same with probabilities for the weather, for throwing a dice, etc., etc. If you would know everything, like the exact movement of the dice, the friction, the way of throwing it, whatever, you would know the result. You would know the number. With qubits, it is different. They are inherently probabilistic. You really cannot know. Not because you lack some information, but because you really cannot know. This qubit really exists in a state that contains both probabilities, both possibilities, 0 and 1, simultaneously. Not one or the other, really simultaneously. This is what we call a superposition. Now, this superposition is not what we can see, but we will come to that later. The real power of qubits, and thus the potentially real power of quantum computers, emerges when many qubits interact. Then the size of the quantum state actually grows exponentially. If you scale them up, let's say we take n qubits from now, n qubits together can be in 2 to the power of n states simultaneously, which can give you a crazy advantage in speed compared to a classical computer. Imagine looking for the way through a maze, and instead of going one path after the other, you basically do all at once and you choose the best one, your way out. Amazing, like it's really amazing. And 2 to the power of n really scales like crazy. I know for the first numbers it looks kind of slow, but try it with your calculator. Like 20 qubits already require more than 1 million amplitudes to be described completely, and 50 qubits become really difficult to be simulated on a classical hardware. Now, it's obviously not that simple, but we should be used to that in quantum physics already, right? A high frustration tolerance is pretty important in my field. But let's stay positive. I recently listened to a talk from Professor Monroe, one of the co-founders of the companies IonQ, which, as I mentioned, among other companies, work on developing quantum computers. And he had a really cool way of describing the two golden rules of quantum mechanics. Rule number one is what we have basically discussed already. Objects are waves. They can be described by the wave function that we have written down before. And they can be in a superposition. Now, rule number one holds as long as you don't look. If we go back to our Bloch sphere, the moment you measure a qubit, the moment you look at it, you will not observe both states 0 and 1. When being measured, the qubit yields a definite classical outcome, so either 0 or 1. And the quantum state is basically projected onto that result. This is often described as the collapse of the wave function. So, the moment we measure the qubit, the situation changes. We never observe a superposition directly. We either observe 0 or 1, and the probabilities for this are determined by these amplitudes. Basically, in Schrödinger's words, the moment you open the box with the cat, you will find out whether it is dead or alive. But before that, it really exists in both states at the same time. Now, as long as the cat is not a real cat, but some quantum object, of course. And yeah, this is not how everyday intuition works. But at a quantum scale, nature simply does not follow classical rules. There is another really great aspect of qubits, and it is that two or even more qubits can become entangled. That means they are forming correlations so strong that the system can no longer be described in independent parts, even when physically separated. Imagine you had two correlated quantum dice. So you have them near, correlate them, and then you put each of them into some box, and you keep one and send the other to the other side of the world. Okay? These two quantum dice will stay correlated. And their outcome, when you look at them, so you look at one of them in your place, and some other person looks at the same and at the correlated dice on the other side of the world, and those two dice will give you the exact same state. Or in general, their results will be correlated. Their results will be connected to each other, no matter how far away from each other they are. And don't feel bad if you don't feel comfortable with that. Einstein himself called that a spooky action at a distance, so he didn't really like it. I have not gone into too much detail, but mathematically, qubits are described via individual wave functions, so you can really imagine this as a wave. And for entangled systems, this is basically a joint object describing the whole system at once. Okay, so those qubit states, imagine our little Bloch spheres again, those qubit states are fundamentally linked, and they cannot be described separately. anymore when being entangled. So, entanglement, it's often described as a mysterious connection between particles, but mathematically it really simply means that this combined quantum state cannot be written as separate states for each qubit anymore. This system has to be described as a whole. In his talk, Professor Monroe had this really great analogy of quantum entanglement, which I would love to share with you. Imagine this optical illusion with two dice. Now, depending on the angle from which you look at the dice, you could see the front surface either pointing down or pointing up. If I now draw a little dot in the corner, it would thereby be either in the front or in the back for you. Depending on how you look at it, like from which angle, etc., etc. So this means like how you basically measure it. So if I draw this little dot, it could be in the front or in the back, and this depends on the way you look at it, so how you measure it. Now, if you have two correlated quantum dice here, you can again see this dot either in the front or in the back. But most probably, you will see the dot in the front or back for both dice simultaneously. And this exactly means that the measurement outcomes are correlated. So they're entangled, roughly speaking, of course. And that's basically it for the qubits. In principle, these rules are why quantum computers are fundamentally different from classical computers. It's really not about faster laptops. It's a completely different way of processing information. Now, it's not that easy and amazing as it might sound. The challenge with qubits is that they, as quantum states, are incredibly fragile. So tiny disturbances from the environment can destroy the quantum state. And we call that decoherence. Decoherence is what makes qubit fabrication and quantum computing research in general a highly interdisciplinary challenge involving engineers, physicists, and computer scientists working really closely together. You basically need to isolate your qubits from everything possible, from thermal vibrations to other noise sources, which is why we have to cool down the quantum processors, keep a very, very high vacuum, etc., etc. However, if you want to process information, of course, you will need to talk to your qubits. So you cannot perfectly isolate them. Yeah, it's a mess. As a scientist in a lab, you really just fight for your qubit to survive. And then there is a little piece of dust or a heat leak or whatever, and everything breaks. Yeah, been there, done that. It is what it is. Okay, you might think like all of this sounds kind of cool and the little scientists have something to play with, but why should I care? Qubits are not important because they're strange. They are important because they allow entirely new technologies, like quantum computers. They may solve problems that are intractable for classical machines. They can help in optimization problems, in drug discovery, in so many possible fields. And I'm pretty sure there are actually more fields to come. Quantum communication can distribute information with fundamentally new security guarantees, which we might need because quantum computers could break our current encryption, but I can do another video on that. And quantum sensors can achieve unprecedented precision, most probably never achievable with classical means. So there is really a ton of great application of quantum technology. And currently, mostly theorists are working on introducing new quantum algorithms, which are supposed to beat classical ones when it comes to speed, power, precision, etc., etc. I actually do plan on making an own video on that. Okay, let's get some take-home message for you. A classical bit chooses between 0 and 1. A qubit lives on an entire sphere of possibilities. And from that very simple idea emerges one of the most powerful technologies that we as humans may have ever attempted to build. Now, with that, enjoy your weekend and maybe brag with your new knowledge at the next dinner party. See you next time. Bye.